this really stimulating conference. It's been really enjoyable. And I'd like to thank them for the opportunity to talk a little about my research. So I'm going to be talking about quantum oscillations in the underdoped cuprates, specifically whole-doped YBa Cu. I'm actually not going to give too much of a pedagogical background because I'm going to try and just give you a flavor of the progress in the field, in the actual experiments that have been done, and how the understanding has progressed over the last few years. But hopefully you should be able to pick up as we go along. And this is our collaboration. All these experiments are done in high magnetic fields, as you'll see. So several of our collaborators are at the high magnetic field laboratories at Los Alamos and Tallahassee. The crystals are single crystals grown in UBC, and these are my Cambridge or ex-Cambridge collaborators. Okay, so most of you are probably familiar with the high TC phase diagram, and chiefly the region which is of interest to us for looking at the normal state, or where the normal state is particularly unconventional, is the underdoped region here. So in the overdoped region, we think we know that this is similar to a Fermi liquid, so there's not that much that is particularly puzzling about this region. And in the very underdoped region, we know that this is an near antiferromagnet, and one can probably treat this as a doped Mott insulator. It's in the region in between where we're not really sure what the ground state is if there was no superconductivity. So the high temperature superconductivity itself is one of the mysteries as to why the superconducting temperature is so high, but the other mystery, possibly the even more puzzling question, is why is the normal state out of which superconductivity develops, why does that have so many anomalous properties? And so that's what I'm going to be talking about today. And the region we're going to be studying, so we're going to be studying the whole doped cuprates around this doping region between around 8 to 11%. So what do we know in this field? So this field has obviously been around for a long time. It's been around for more than a couple of decades before the advent of quantum oscillations. So what did conventional wisdom, before any of the quantum oscillation experiments started being done, what did that tell us? So just very, very briefly, the main things, with relevance to the electronic structure, two of the things which we know, one is that there seems to be an antinodal gap. There seems to be an absence of density of states at the Fermi energy by quite a significant amount. The density of states lies quite a way down, about 50 MeV, below the Fermi energy at the antinodal regions. Also, it appears that we seem to be departing from Fermi liquid physics. For example, in photoemission experiments, at very low temperatures, one sees a sharp quasi-particle peak from superconducting coherent particles, but as one goes to higher temperatures, one loses this sharp peak, which seems to indicate that one doesn't have quasi-particles anymore. And that's just photoemission. I'm obviously just picking up a couple of the things which are relevant to the electronic structure and mentioning those in particular. Similarly, in optical conductivity, in C-axis optical conductivity, one sees a gap in the coherent spectrum, so this indicates an antinodal gap. And one also sees that this doesn't recover at higher energies, which it would if it was a more conventional gap. So the sum rule is violated. This number would be 1. So this is just a ratio of how much of that lost space we're regaining. So this indicates that something unconventional is happening. We don't just have a simple state in which one can treat this as a Fermi liquid and then look to see how superconductivity develops out of it. So this was the state of play up to about 4 years ago, which is when quantum oscillations were first seen. And so I'll just come back to this in a second. So it was quite surprising when quantum oscillations were seen, because considering that this material has not been thought of as a Fermi liquid, as having very little to do with a Fermi liquid, it was very surprising when in 2007 Louis Taillefer, working in the high field lab at Toulouse, discovered these quantum oscillations. So what exactly do quantum oscillations mean? A 2-slide tutorial on it is that essentially if one has say, Fermi gas, or we normalize Fermi gas or Fermi liquid, and one puts that into a high magnetic field, one obtains quantization of Landau levels. So the particles, the electrons, can now travel only on quantized orbits instead of a continuum in momentum space. And so if one takes constant energy cuts in momentum space, one obtains a topology of a surface along which electrons can travel. One can have multiple cross-sections of the surface, and at a simplest level, what quantum oscillations tell us is, at a very simple level, what is the topology of the surface, what are the orbits along which electrons are traveling. If we have large and small frequency quantum oscillations, okay, if we have, I'm actually, let me see.
So I'll be talking about this in the cuprates, but this is just to sort of, for you to keep in mind that's what we'll be talking about.
So the extremal orbitals dominate the signal.
Thank you. Okay. On the overdoped side, one has a large Fermi surface, characteristic of what one would expect for a paramagnetic band structure. So this is what one would expect in a large Fermi surface, and I'll just show you on the next slide measurements that show you that. The fact that we saw a frequency of 500 Tesla indicates that we're looking at a closed pocket which is considerably smaller in area than what one saw on the right-hand side of the overdoped regime. So just to give you an idea of how much slower it is, these are the oscillations of overdoped Thallium-2201. So the question TDR is asking, there are many more oscillations here, so this peak is much narrower. It's only because our oscillations in underdoped cuprates are that much slower. And the size of our pocket, hence the size of the frequency, is about 35 times smaller in the overdoped thallium. So this is what is seen in measurements by Nigel Hussey et al. In overdoped Thallium-2201. So one sees exactly what one would expect, a paramagnetic Fermi surface from band structure calculations, but we see something where a lot of area has been lost. So clearly the ground state is different. The question is, how exactly has it changed? And something to point out is that, interestingly, that the area reduction is in some ways similar to what one sees in photoemission. One sees a full density of states at all regions of the Brillouin zone on the overdoped side. On the underdoped side, a lot of that density of states has gone away. One only has a small remnant density of states. So there are similarities between the change in the density of states accessed on the overdoped and underdoped side. Exactly what this means is not as simple. It's not a question with a simple answer. The other obvious conclusion we can draw is that there are multiple frequencies. One can see the speed structure. There are multiple frequencies, which indicates, one can see this here, which indicates either that we have multiple pockets or that we have a single Fermi surface with more than one extremal orbit that's possible on it. At this point, just from looking at the data, we can't tell which of the two possibilities is the right one, but it has to be something that gives you more than one frequency.
But there is one dominant pocket. Is that fair to say?
No, one cannot conclude this from this information. The amplitude is bigger, but that doesn't mean the pocket is dominant. It could be each of these are separate pockets. It could be one with. At this point, we can't tell. We have to do some more work. Okay. So those are things we can extract directly from the data. We don't need to do any more measurements or add any more interpretation to it to address those questions. However, there are more complicated questions. The question of, is it a single surface or multiple surfaces? Is there a single carrier or multiple carriers? This is something we have to work more at. And the other one is, one of the things to note is that quantum oscillations don't tell you where these density of states are located in momentum space. It will tell you how much, what the area of the pocket is and what density of states one is picking up, but it doesn't tell you where that is. And so these two pieces of information are something we will try to infer, and I'll try to convince you as to how I've arrived at what I think are the answers to these two questions, but those are more indirect quantities. Okay, so why is it that one even thinks that there might be multiple carriers? It could have been that we have a whole doped material, the carriers should perhaps naturally be holes. One of the reasons why this is a question that needs to be addressed is that measurements of Taillefer et al. Indicate that the oscillations are seen in the negative hole resistivity. If you look on here, these oscillations are seen in the hole resistance, and they're on the negative side, which a simple interpretation, if one were to ignore things like vortex liquid physics, a simple interpretation would lead one to conclude that these are electron-like carriers. So if one has to have electron-like carriers in a hole doped cuprate, there must be holes somewhere else, so one would have to invoke a density of states which contains both electrons and holes at possibly in different parts of the Fermi surface. Accordingly, these results that implied that electron carriers were present in the Fermi surface led to a host of theoretical models which tried to explain this, all of which place the electron pockets at the antinodes. And so these are a few of the models. Some of these invoked large Q, so this invokes a stripe model with a large Q possibly accompanied by a charge ordering wave vector as well. So this is a spin stripe with a charged component. This would be true either for a d-density wave or a spin density wave with a large Q, close to pi by 2, pi by 2. Close to pi wave vector. And this is a more recent model which invokes a low Q, so this invokes charge stripes with an additional nematic. What's common between these is they all place, for symmetry reasons, they all place the electron pocket at the antinode. The holes are either distributed in open sheets at the nodes or in closed pockets at the nodes. But there are certain features that are common to these. Now obviously, this raises a question, this poses a conundrum. If any of those models were to be right, one would have to address the question of, first of all, you have a big superconducting gap. Second of all, whether or not this is the same as that gap, one has an observable antinodal gap. And can magnetic fields starting from 22 Tesla really close this gap or in some way change the system and cause a density of states to arise at the antinodes? This is, of course, one of the pressing questions that arises were one to invoke any of those models.
Question.
Yes.
What is the largest mean free path in your best system?
The order of 100 angstroms?
100 amps.
Yes. 100, 200, but around
So
about
any
there.
stripe or anything should demand ordering.
I'm not sure if there's a vigorous answer to that question. Yes, at least that much, on that scale. Yes. Okay. So having the conundrum of, are any of these models right? Does one have electron pockets and hole surfaces? One of the questions we can try and address are there actually multiple sections of Fermi surface, or is there only a single section? Are there multiple carriers, or is there only a single carrier? I'm going to try and go through this rather fast, and you can ask me more questions, but the chief idea is that one can have quantum oscillations in broadly one of two ways. One way is which typically one has more than one surface, especially in three-dimensional systems. If one has more than one component to a density of states, if either one has multiple pockets or a pocket accompanied by open sheets, one can have particles that oscillate between the different components of your Fermi surface. If that were to happen, the chemical potential is largely held constant, and the oscillations are chiefly in the number density. In that case, this is what we all know and love. This is what we're familiar with most of the time. In that case, this is what I spoke about when you apply a magnetic field. The size of the cyclotron orbits grows, and as they leave the Fermi energy, one has a sudden discontinuity that happens at half an integer lambda level. Why this is important is that this tells you what you expect the phase of the harmonic to be with respect to the fundamental, and you expect the harmonic to line up with the fundamental on the rising side. In contrast, if one had a system comprising chiefly of a single pocket, without another component for electrons, for particles to flow between, in that case, one can't have a chemical potential that's fixed anymore. Instead, the chemical potential itself oscillates. In this case, the Landau levels are pinned to the Fermi energy, and as the magnetic field is applied, the chemical potential itself moves, and in this case, the discontinuity is when the Landau level becomes completely full, and at that stage it empties all of a sudden. So the discontinuity here is at an integer Landau level. And why this is important is that in this case, the harmonic lines up with the fundamental at a phase of 180 degrees, out of phase with what one would have expected for the case where one had multiple pockets. So one sees here the harmonic is lined up with the fundamental on the falling side. So they're 180 degrees out of phase. Okay, so this is now data. This is torque data, and this is contactless conductivity that's just integrated to have the same type of phase. So what we spoke about here would have been a thermodynamic quantity. So this is for the magnetization. So if you look on here, you can see that actually the harmonic and the fundamental, the harmonic is in purple, the fundamental is in green, and so you can see on all of these curves, these two are at about 0 degrees, and this is at a higher angle. All of these curves, the fundamental and the harmonic come together on the falling side, and that actually is a first signal that what we're seeing is not what one would expect for number density oscillations, but what one would expect for chemical potential oscillations, which seems to indicate that we have chiefly one surface as opposed to multiple, at least multiple equivalent surfaces. Equivalent meaning contributing equivalently to the density of states. But obviously we need to check this in detail before we arrive at such a drastic conclusion. So to do this, we look at what one would expect for the harmonic in the case of a contribution to chemical potential oscillation. So this term here is what one expects just for the standard number density oscillations. The term here is what one would expect for chemical potential oscillations. And so the way one can determine whether this term exists is to look to see if you have an amplitude that goes as a square of the amplitude of the fundamental. So that's a smoking gun to tell if we do have chemical potential oscillations. So firstly, this is the angular dependence of the fundamental. If it was number density, one would expect this blue line. If it was chemical potential, the data is actually these red dots on here. And you can see it looks nothing like what one would expect for number density oscillation. Instead, the black dots on here are what would be predicted for the square of the fundamental amplitude. And you can see the red dots on here are actually the amplitude of the second harmonic, and this lines up extremely well. So this is a fairly compelling argument that we are seeing oscillations of the chemical potential. One can also tell this from the temperature dependence and from the field dependence. The line on here is the harmonic, the dots on here are the square of the fundamental. You can see good agreement. So this both tells you that you have a single carrier, which is the only way you will get this square dependence, and that there's chiefly one Fermi surface section. To try and put a bound on how much contribution you could get from anything else, we do a quantitative comparison of the size of the second harmonic with the size of the square of the fundamental. And what we get is that the single pocket that dominates the density of states almost dominates it completely. There can be up to a 30% contribution to the density of states from anything else that contributes to the density of states at the Fermi energy, be it chains, open sheets, other pockets. You can have up to 30% from there. And this is an error bar, so it could be that it's chiefly one pocket. Okay, so that pretty much rules out all these models in which there are multiple sections which contribute similar amounts to the density of states at the Fermi energy. It's possible that one could still keep one of these alive if one of the other sheets has a very light mass and contributes a small amount to density of states, but that would have to be a very stringent constraint. One could not have two pockets with equivalent mass, and one actually could not have two closed pockets of opposite carriers. Those are very strictly ruled out.
Quite apart from two-dimensional models,
Yes.
even the band structure would have said there should be chain bands.
Yes, and so that would be, if that was at the Fermi energy, that would be within 30%. That is what you would expect. So that doesn't contradict. Okay, so now that we've concluded that we have chiefly a single Fermi surface section contributing to the density of states at the Fermi energy, the next question is, where is this located? How much time do
You have about 10 more minutes.
Okay, so the next question is, where is this density of states located? First of all, the fact that our quantum oscillations go down to 22, possibly lower, in magnetic fields, so we actually don't lose the quantum oscillations. It's just that the flux jump noise gets high. That's the experimental limitation. So very likely the oscillations would go down even lower in field. And considering that the amplitude of the oscillations at a very simplistic level would scale perhaps as the square of this gap, it would seem quite hard that if one had only one section of Fermi surface, that would be at the antecedent. So that argues for it likely being at the nodes. The second argument one can make for it being positioned at the nodes is that through these dopings, the frequency of all these dopings between 9 and 11% doesn't change, but the mass changes quite dramatically, increases by 3 times within a doping range of about 2%. And if one converts this into a Fermi velocity, this is equivalent to a Fermi velocity that collapses quite dramatically, indicating a quantum critical point at around 8.5%. Interestingly, ARPA's results have very recently, until now, photoemission typically extracted velocities from the middle of their dispersion. But if one takes the velocities very close to the Fermi energy, what used to be constant now shows a very similar, this is a different material by the way, this is a bismuth-based system. However, this drop in Fermi energy is in Fermi velocity is very similar to what we see here, which seems to indicate that where both these experiments are looking at the same density of states. So this is looking at a nodal density of states. It's very likely that what we're measuring is also probing the nodal density of states.
But the Fermi velocities are anisotropic, very strongly anisotropic. So what at the node? That's what I was measuring. So
Yes.
you
No, my Fermi velocity is over to the average. Yes. Yes.
Yeah. So this is measuring something in the absence of fields. So
Yes,
sure. This would be the unreconstructed.
Yes, I don't know about if it's unreconstructed. It would be this. It would come from the node here. So I don't know what you would call it, but yeah.
So Suchitra, your mass divergence is coming from hitting the temperature dependence in a Lifshitz oscillation?
Yes.
Okay, and what are those green?
Oh, these I just didn't get into more detail.
Yeah.
This is the resistivity upturn. So essentially where this comes down is also where insulating behavior starts. That's just additional
But
physics.
then you have a TC under the insulator, so
That is correct. I don't think it's an insulator. I think it's a bad method. Yeah, sure. And I think Arthur also sees a gap over sometimes. Sure, okay. We can go to our gap. Yes.
So the velocity measured in office,
Yes.
is that a function of the
That's a good question. I actually don't know. I think that's at the lowest temperature. I don't know. Okay. And yes, the one additional argument for the density of states being located at the nodes, this is more of a consistency check as opposed to a direct argument. It's quite interesting that we have this characteristic pattern of a central dominant frequency flanked by two side frequencies split by 90 Tesla. And this somehow seems characteristic. It seems one could just get this by invoking types of warping or types of components, but it seems rather characteristic, and the question is how would we get this? One quite simple way to get this, if you had a nodal pocket, this is just an illustrative shape. It could be a different shape. It could be this shape. It could be whatever shape you want. But if you had a symmetric pocket at the node, we haven't really looked into detail to bilayer splitting, but if one invokes bilayer splitting, as has been resolved by photoemission experiments in YBa Cu, this single pocket would be split into two pockets of slightly smaller and slightly bigger area. Now this would happen both at the nodes and at the antinodes, but that would lead to only two frequencies, which is why it took us a while to figure out what was possibly happening. However, if the pocket is at the nodes, the size of the bilayer splitting is much smaller, it's about 10 times smaller than what one would expect at the antinode, which means that not only would you get those two frequencies, those two orbits, one would also get a breakdown orbit, which involves a particle tunneling between these two parts, and the area of that would quite naturally be an average of the two bilayer split areas. So this is a very natural way to see how one could get a central dominant peak and two frequencies on the side that flank it. And this is just to show that with a pocket of different shapes, one would essentially just get fewer breakdown points, but very similar physics. And one just has one variable in that case, which is the size of the bilayer splitting, which would give one a magnetic breakdown field. And using that single variable to simulate this, the red and blue curves are the simulated data from these models of a nodal pocket with a bilayer splitting of about 10 MeV, and the black is the observed data. So one can see this is quite a simple way to get it. It may or may not be the right way to get it, but it's quite a simple way in which one could obtain this form. It's also consistent with the bilayer splitting actually measured by photoemission. So that's a good consistency check. Okay, so it's suggested that this pocket is located. It's suggested that this pocket is located at the nodes. Let's see what are possible models that could give rise to this. Something we're all familiar with would be just standard antiferromagnetism. And if one were to make it incommensurate, one could obtain anisotropic pockets, which would give a lower density of states more consistent with heat capacity. A couple of possible issues are, first of all, in the doping range study, this order hasn't been observed as yet. And secondly, it's not obvious how one would get a negative Hall effect from this kind of model. Other models involve possibly obtaining these pockets in the absence of translational symmetry breaking. I'm not actually sure as to the exact predictions of this model for what we see. Maybe Morris can tell us more about that. And something else I'm going to discuss quite briefly is another possibility, and that's following on from recent NMR measurements, which see a low Q density wave, a low Q form of long-range order, and their interpretation of the line splitting which they see is for a periodicity along one direction. Now, if we only had Fourier periodicity along one direction, we couldn't get closed pockets, we would only get an open sheet. So if I were to consider that there could be Fourier periodicity in two directions, either in the form of stripes on different layers, or possibly just a higher amplitude along one direction as opposed to the other, as there might be preliminary evidence from SEM or zero field X-ray measurements, which haven't yet been done in field. What I could then do is to come up with a model which could give me a pocket at the node, as you'll see. So these are a small Q wave vectors. So if I take my electron moving along particle, let's say. So I take the anti-clockwise direction as positive Hall polarity. So the particle moves along this way, it gets Bragg reflected, and then I translate the section of the surface there. So this is just a very simplistic way of showing you what I would get for a bidirectional low Q model. So I go along the entire route and join back up, and this is the pocket that I would get. Obviously, I've taken commensurate Q, I've taken very simple assumptions, but to show you in the absence of a full-blown calculation, what I would obtain is a pocket located at the nodal region. Interestingly, the polarity is now clockwise. So what one would expect from here is a polarity opposite to that of the original Fermi surface. So if this was whole-like, one would expect this to be electron-like character. And why that's happening is because the Brillouin zone is a quarter times a quarter, which is 1/16, and the particles practically fill up the entire of this reduced Brillouin zone to give you this small nodal pocket. This is just a possible way of obtaining a nodal pocket. It has some good things about it. One is that the area is about right, which would be about the size of the dominant quantum oscillation, which is about 530 Tesla. It would be not too far from the size of the arc. This is drawn to scale. One thing it does explain rather well is how one sees this quantum critical point here. If this is from charge order, NMR sees, well, NMR neutron scattering see spin order begin at this 8.5%. So going from charge order to charge plus spin order, this would be a natural way in which one gets a density wave transition and a quantum critical point here. Also, having a single pocket is quite good because a single pocket for bilayer gives us a density space of about 5, which is similar to that measured by heat capacity in high magnetic fields. And of course, this also satisfies the criteria that we just have a single dominant pocket contributing to the density of states. Because the polarity is opposite, it also gives us a negative Hall and Seebeck coefficient as measured by Louis Type. So that's just a possible way of reconciling. So basically, I told you things we can extract pretty definitely, incontrovertibly from the experimental data. Other observations which a single pocket is almost certainly true. A nodal pocket is quite definitely suggestive, if not unambiguously, but it's definitely suggestive. Taking all those criteria into account, this is a possible way of explaining it. There could be many other ways, but any possible way of explaining the quantum oscillations would need to explain all the measured data, not just a subset of it. Relation to the pseudo gap, that's not an easy question to answer. And one possible way one could look at it, of course, the photoemission experiments are measured at zero fields, quantum oscillations are measured in a field. We're measuring solely at low energies, we're only measuring at the Fermi energy. Other experiments measure at high energies. So is there a connection or not? Possibly. It's possible that the small pocket that we see is related to the small density of states seen by photoemission, but obviously there's a lot that is not yet explained and needs to be explained. Thank you.
Question about your vanishing velocity here at the onset behavior.
Yes.
And my question is, wouldn't the effect a temperature-dependent Dingle factor? If you have a linear to resistivity, the Dingle factor could...
That's a good question. It's not something that can be ruled out. I think the fact that, it's a fairly good consistency check that photoemission as well sees a velocity that goes down there. But a priori, just from quantum oscillations, it's not something I can rule out. But I think the fact that photoemission also sees it would seem to suggest that's not the origin. This is not a regular shape. This is a zero correlation model. So as soon as you put in this is going to get rounded.
By what?
Correlations, for instance, if anybody affects rounded. I've just drawn arcs here. This is not an actual pocket shape. This is a cartoon.
Okay. I asked. So the temperature dependence of the amplitude, I think it is due to a number of factors,
yes.
Right? Can one uniquely focus on the Fermi distribution as the only thing? I mean, there is some Dingle temperature factor. I mean, there are all kinds of things.
Yes, one can do that for the temperature distribution, yes, because that's in a certain place. So that, to check Fermi Dirac statistics, yes, that has been done very rigorously. if I was able to do it to that precision at all the dopings, I would have a more certain answer to Morris's question. But I lose resolution as I go closer, as my mass increases. That's why I don't have as certain an answer to Morris.
And so I'm wondering, do you see any field dependence to the frequency?
Yeah, this is a good question. There's no drastic field dependence. There are some frequencies that become more prominent at high fields. It's not yet clear to us whether there's a qualitative change or this is just an exponential increase with the field. But there's nothing that looks like a transition or an obvious change. Any change is subtle.
So also, do you know how far do you have to go before you run out of Landau levels?
Yeah, we're not, I think we need to go to like thousands.
Thousands?
Yeah, if you go to, I can tell you from my first slide, but yes, one would need to go to about 1,000, yeah, so on here will tell you, yeah. So basically we're at level 6.
Okay, I have two more questions. I don't know if did you mention an effective mass?
That's a good point. I probably did. It's around 2 electron masses.
So how does it compare with band structure predictions?
It's not too heavily renormalized by about 4 times. You would get about 0.5 from that.
I have a more general question. In the old days, at least, people would do positron annihilation to study dirty metals. Nobody does that anymore. Is that because there are no facilities, or?
I think it's been tried.
Actually, the positrons
Is there a
go
more
to the
fundamental
chains.
reason?
Yeah, the positrons go to the chains and give you no information that you want in YBCO. So I'm going to ask one question. So the reconstructed Fermi surface that you have, you said there was only one per bilayer, or did I misunderstand you?
No, sorry, it's one per plane.
It's one per
Yes.
plane. And even if you take one per plane and the magnetic breakdown and stuff like that, you can still agree with Bobinger's magnetocaloric?
It's not too far. I don't need to take any magnetic breakdown. It's still just that.
Okay.
Yes, you would get about 5 if...
With the factor of 2 in place?
Yes.
Okay.
You get about 5. Which is why if Bobinger takes 1 per chain, he gets about 2.5. So it's, I can show you how those numbers work.
So it depends on whether you include this or not. So the value which Bobinger gets is somewhere between 5.5 and 3.5, depending on whether you take this gamma 0 or not, because it's not clear where it's coming from.
Yes.
So 5 is not too wildly off. I would say it's within a margin of uncertainty.
Well, so if there are no further questions, let's thank Suchitra.